thank you for attending this webinar. So if you're like me, you've been using relational databases for as long as you can remember. Back in the 90s, I used Oracle and Microsoft SQL Server. And then in more recent years, I've used open source databases like MySQL and Postgres. Relational databases were simply the place to store your data. And there's very good reasons for that. So one reason is because SQL is a nice, high-level, declarative query language. You simply express the data, what data you need, and then the database server figures out how to efficiently retrieve that data. You don't have to worry about low-level storage operations or anything like that. You're abstracted away from it. Another reason why relational databases are a success is because they provide ACID transactions. You know that if you perform a series of updates, then those updates will either be applied in their entirety or not at all. The consistency of your data is maintained. That provides a nice, simple programming model. And there's also other good features like constraints that you can define that protect the integrity of your data against application errors and so on. So relational databases just have all of these nice features. But over the past few years, we've seen growing interest in an entirely different kind of database, the so-called NoSQL database. And part of that is due to the requirements of these incredibly high-scale consumer-facing websites like Facebook and Amazon and so on. And as you're going to see, in some scenarios, NoSQL databases offer much better performance and scalability than relational databases. And then there are also these NewSQL databases that are relational databases with ACID transactions and so on, but they have a different architecture that enables them in some situations to have much better performance and scalability when compared with a traditional relational database. So over the past year or so, I've been porting use cases from my book, POJOs in Action, to various NoSQL databases. And then in more recent past few months, I've been porting them to a NewSQL database called VoltDB. And in this webinar, I'm going to share with you my experiences, what worked, what was easy, what was straightforward, and also what was extremely difficult. And so as you're going to see, it's a real interesting mixed bag of benefits and drawbacks. So for those of you who don't know me, I'm Chris Richardson. I actually grew up in England, and then 20 years ago, I moved to California. I got my start in my computing career programming in Lisp, implementing compilers and runtimes and GUIs and frameworks and so on for the Lisp, an early dynamic object-oriented programming language. Eventually ended up programming in Java, and then about 6 years ago, I wrote the book POJOs in Action, which is all about how to build applications with frameworks like Spring and Hibernate and so on. And then back in 2007, I started playing around with cloud computing. That turned into an open source project, Cloud Tools, which then turned into my startup, Cloud Foundry, which was then back in 2009 was acquired by SpringSource shortly before it was acquired by VMware. And there was this nice graphic from the register showing these three fish, but sadly they were not drawn to scale in terms of market cap. So in these days, I'm a developer advocate for Cloud Foundry. So in this talk, I'm going to first begin by providing some of the motivations behind NoSQL and NewSQL databases and why they might be appealing to developers like us. And then the bulk of the talk is really a case study about taking code that was written originally for a relational database and porting it to these NoSQL and NewSQL databases. And I'm going to begin with just looking at basic primary key access and how you can map entities from your domain model to these to the NoSQL and NewSQL databases. And then later on, I'm going to finish up by looking at how you implement queries. And as you're going to see, for some databases, that's not an entirely trivial thing to do. So in the book, the sample application was Food to Go, which was a takeout or takeaway food delivery application. Customers would place orders for food at the website, and then it would be delivered at the specified time to their home and office. So that you could imagine, as you could imagine, back in 2006, that application relied heavily on a relational database. All of its data was stored in MySQL or Oracle, and the book talked about JDBC and Hibernate and all those good relational technologies that we're used to. And it worked pretty well. But you could imagine that, say, 6 years later, if that was a real startup and they had been successful, they would have had to have dealt with a number of growth-related challenges. They would have had to deal with increasing traffic, increasing transaction volumes. They'd have to deal with increasing data volumes. They'd probably want to spread their application across multiple data centers, both for high availability, so they can have a disaster recovery strategy. You know, if one data center gets hit by a hurricane or an earthquake or tornado or some natural disaster, but also in order to improve the user experience by being closer to their users, so reducing network latency and so on. And then also they'd have to deal with increasing domain model complexity. So these are all pretty typical challenges that successful companies would have to face over time. But the problem they'd run into is that they'd sort of very quickly, when trying to solve these problems, run into limitations of relational databases. And what are those? Well, firstly, relational databases have real issues with scalability. Typically, the horizontal scalability, like being able to run them across multiple servers, is somewhat limited. And as a result, you typically have to scale vertically, which at a certain level becomes incredibly expensive as you move away from commodity servers and you have to use high-end servers. They also tend not to be easily distributed across multiple data centers where you've got a database master running in each data center and with data being replicated between them. That tends to be a non-trivial thing to do. Schema updates tend to be another challenge. On the one hand, you can just simply add a column to a table by doing alter table, add column, and so on. But what if that table is large? It could very easily take many hours to update each and every row in that database to add that new column. And so at some point, that could actually become somewhat impractical. There's also just the classic object relational impedance mismatch problem, where on the one hand, you've got your rich domain model with relationships and inheritance and so on. And then on the other hand, you've got your flat relational model where you've just got foreign keys. How do you map from one to the other? And, you know, obviously tools like Hibernate and JPA solve that, but in general, that's quite a difficult and sort of an unsolved problem. And then there's also the issue of semi-structured data, entities that have a varying number of attributes. That doesn't fit very well into the relational world where you've got a fixed predefined set of columns. So that's another challenge. So what can you do about it? Well, on the one hand, you can just spend money. You can take your commodity server and you can put in lots of memory. You can put in SSD drives. And because of Moore's law, that will actually get you quite a long way. I mean, today you can, for a modest amount of money, you can buy a very high-end server, or what would be considered a few years ago to be a pretty high-end server, quite cheaply. But at some point, that only gets you so far, and then you end up having to buy Oracle and very high-end servers, and that ends up becoming very expensive very quickly. And that's on the slide. I have a picture of Larry Ellison's former yacht, and you know, you're sort of having to give him a lot of money and subsidizing his yacht buying. So the other option is to spend money on people and take commodity hardware and open source databases and build out your own highly scalable distributed database infrastructure. But that takes a lot of people and a lot of time and a lot of effort. So either way you're having to spend money. So another option, which is the focus of this talk, is to use a NoSQL database. And as you're going to see, for certain use cases, they can give you much better performance, much better scalability. They also tend to have a richer data model, which can solve which sort of eliminates the object relational impedance mismatch problem, and they tend to be schemaless as well. So the problem of having to update large tables effectively goes away or transforms into a much easier problem. But on the other hand, there's no such thing as a free lunch, and so you have to give up something. And what that tends to be is ACID transactions. As you're going to see, NoSQL databases tend to have pretty limited transaction models. And you have to tend to give up on database consistency as well. There's a whole topic of eventual consistency and so on. And you tend not to be able to define constraints on your data. So it's sort of a different model. So one of the databases I'm going to talk about today is MongoDB, and that's a document-oriented database. And what that means, at least in the context of Mongo, is that a document, which is its unit of storage, is actually a JSON-style document. So it's an object that has a set of name-value pairs, and the values can be primitives, strings, numbers, etc. They can be lists of other documents or primitive values, and they can also be, values can also be maps, or lists of maps, or objects. So it's a recursive data structure, which can, one document can actually contain quite a lot of data. And it's also schemaless as well. So you can have a collection of documents, but they don't have to have the exact same identical structure. Transactions in Mongo are just limited to the update of a single document, so you can't update two documents atomically within a single transaction. That feature is just not available. It's got a rich query language for dynamic queries, which is quite nice, quite different from some other NoSQL databases. It's not SQL, but it's quite powerful. It also has tunable writes, where you can sort of, for every write operation, you can kind of decide whether you want just speed or you want reliability. Don't really have time to go into details, but it's a very distinctive and powerful feature of Mongo. It's also highly scalable and available. You can transparently shard or partition your data, and you can also have replica sets that are a generalization of master-slave relationships with automatic failover. So if the master goes down, the remaining slaves talk amongst themselves and elect to do master automatically. And there's various use cases for Mongo. One of them is just high volume writes, where you need to blast data into the database, like for logging, or analytics, etc. Mongo is good for that. Mongo, because of its document model, is also good for storing complex data. Rather than having to sort of denormalize or normalize the data and spread it across multiple tables and multiple rows, you can represent a complex data structure as a single document that's persisted very efficiently inside Mongo. And also, it's very good for storing semi-structured data, where you've got varying attributes in your entities. So that's good. So then another database, another NoSQL database I'm going to talk about is Cassandra, another open source project. That actually has a different data model. It describes itself as a column-oriented database, which I don't tend to find as a very useful description. But what you can think of the model as is each row in a Cassandra database is basically a map, a set of key value pairs, which are actually sorted in increasing order of key value. And we'll look at that more in a minute. Once again, transactions are limited to the update of a single row, so no full ACID transactions. It's got very fast writes. So at one point, writing to Cassandra was actually faster than reading out of the database, which was quite interesting. It also lets you tune reads and write operations on a sort of per operation basis. So you get to pick, do I want to see consistent data, which could actually take a long time, or comparatively long time, or do I just want to get some data and I don't care if it's the latest version of the data. So you get to make that choice on a per operation basis. That it can be quite useful. It's also incredibly scalable. you can build a cluster that can be spread across multiple data centers, and you can just keep adding servers to it, and the cluster and the data gets dynamically repartitioned, and it just keeps growing, scaling and scaling and scaling. And people have built very large Cassandra clusters. It's got a CQL that's an SQL-like language that can be useful in some situations. And there's various different use cases for Cassandra. Because it scales, it's very good for dealing with big data scenarios. It's also very good if you need to distribute your database across multiple data centers. It's also very good at write-intensive applications like logging, where you just need to blast data into the database. And it's also good in scenarios where you have high availability, where you just need to always be able to write to at least one database server. Because there's some features that I can't go into. Its architecture is such that it has very high availability when it comes to writing. So there's a bunch of really interesting use cases there. And there's, Mongo, Cassandra, those are two very high-profile NoSQL databases, but there's many more. If you go to NoSQLdatabases.org, there's a list of 100+ NoSQL databases. And I've listed a few of them on this slide. But, if I haven't mentioned your favorite, I apologize. So, one option is NoSQL. Another option is to use a NewSQL database. And as I mentioned at the beginning, these are relational databases that have SQL and ACID transactions, so they seem very familiar. Yet at the same time, they have a different architecture that gives them much better scalability and performance. And the one that I've been experimenting with is VoltDB. And the man behind VoltDB is Michael Stonebreaker, the relational database pioneer. And he has this really interesting take on the current state of traditional relational databases. And he claims that they're basically designed for 1970s hardware. And so if you think about what's happened to computer hardware over the past 30+ years, it's got a lot faster. You have many more cores, and you have relatively huge amounts of memory. Back when I was in college, the mainframe that was serving the whole of the University of Cambridge, I think had 16 megabytes of memory, right? And today we're thinking of gigabytes or terabytes of memory. So relational database or traditional relational databases were actually designed for a very different world. And his argument is that they can't take advantage effectively of modern hardware. And they did some research. There's a paper, Through the Looking Glass, where they analyzed where a traditional database spends its CPU cycles. And they found that 80% or more of the time was spent in overhead operations, logging, latching, buffer management, and so on. And only a very small amount of its time was spent doing real work. And so what Stonebreaker's come up with is VoltDB. It's an open source database, and it's an in-memory relational database, which is actually, if you dig into it, is quite different than a traditional relational database that you just have you give a lot of memory to. So they've designed it first and foremost as an in-memory database, which makes it incredibly fast. Yet at the same time, it has durability because you can replicate amongst servers. It also has durability through snapshotting, where it writes the state of the database server to disk very efficiently. And then it also logs changes from between snapshots so that you can recover easily. And then it also gives you transparent partitioning or sharding, which makes it incredibly scalable. And folks have done experiments where they had VoltDB running on 39 servers, 300 cores, and they got incredible throughput. So it definitely does scale. But as you're going to see, it's even though it's a relational database, it's quite different from what we're used to. For instance, there's no JDBC. So I think, though, whether you're using SQL or NoSQL or NewSQL, we're moving to a different world where rather than your application just using a single database for everything, different modules of your application are going to use a different kind of database that's best suited for their needs. So if one module needs a relational database, it will use needs ACID transactions rather, it will use a relational database or a NewSQL database, whereas if it's storing complex data structures, it could use Mongo, for example, or if it's manipulating graphs, it could use Neo4j. So sort of use the best database for that particular module's needs rather than just one database to rule them all. And to help out in this sort of in this new NoSQL world, there's the Spring Data project, and its goal is to provide the benefits of Spring, of productivity and portability and testability to this NoSQL world. And there's support for various NoSQL databases such as Mongo and Redis and Neo4j, for example. So if you go to springsource.org/springdata, you can read all about it. Okay, so that's the motivations behind NoSQL and NewSQL. So let's look at how you go about using them. So in the example in my book is in the application, the key use case is place order. And so the customer goes to the website, enters the delivery address and time. The system displays the available restaurants for that delivery address and time. And later on, I'll talk about what that means. The customer picks a restaurant. The system displays the menu. The customer selects menu items and then places the order. So that's the flow. It's pretty straightforward. And you can imagine that behind this, the implementation would have a domain model that looks something like this, obviously simplified and so on. So we're going to have a restaurant entity, that has a name. It has a service area that's the set of zip codes that the restaurant serves. So this was back in 2006, so we didn't do anything fancy like GeoSearch. It also has opening hours that describe when during the week the restaurant is open. And the opening hours is a collection of time ranges, where a time range is day of the week and then the opening time and the closing time. And then also it has menu items, and a menu item is just a name and a price. So obviously this is somewhat simplified, but it's sufficient for our purposes here. You can imagine that if you were using a relational database, you'd have a schema that looked like this. So the restaurant class would get mapped to the restaurant table. The service area would get mapped to the restaurant zip code table that has the zip code and the foreign key back to the restaurant. And then the opening hours gets mapped to the time range table that has a foreign key back to the restaurant and stores the day of the week and the opening time and close time and so on. So pretty straightforward, at least in the context of relational databases. We have a repository, or DAO, that encapsulates the data operations. So we'd have an add method that would persist a restaurant, and a find details by ID method that, given a primary key, loads the corresponding restaurant. And you can imagine that given the database schema I showed, it would be straightforward to implement this interface using JDBC or Hibernate or JPA. Pretty straightforward. But, how on earth will we do this with a NoSQL database? How do we map the restaurant aggregate, restaurant time range menu items, into the database, into the NoSQL database's storage model? And then how on earth do we implement this interface? So let's look at this. So in MongoDB, it's very straightforward to map an aggregate like a restaurant, and along with its service area and its opening hours and so on, to a single document. So on this slide, I'm showing, I've got a restaurant called Ajanta. It's my favorite Indian restaurant in Berkeley. It has a service area that's a list of zip codes. It has an opening hours that's a list of documents that store the time ranges. So it's very straightforward to map your restaurant entity into a document. And then what's nice about this is that, this is stored, this exists in Mongo as not as textual JSON, but as binary JSON. And it's persisted very efficiently on disk as just a sequence of bytes. You've got quite a complex structure that's stored very efficiently, written to disk and read from disk using serial I/O, so it's quite fast. So each restaurant gets mapped to a document like this, and then a set of documents forms a Mongo collection, which sort of plays the role of a table, except that each document, the documents don't have to have an identical structure. I mean, they should, for your own sanity, they should have a similar structure, but they don't have to have the exact same set of attributes. And then a set of collections forms a database, which is like a schema. And then one or more databases runs on a Mongo server. So that's the model. And so as you can see, mapping persisting restaurants is pretty straightforward. So Spring Data supports Mongo. And so one of the things that Spring Data for Mongo provides is a Mongo template, which is very analogous to the JDBC template provided by Spring JDBC. And so it encapsulates all the boilerplate operations for accessing Mongo, including the mapping of your domain objects to a Mongo document and back again. So in this example, you can see we've got our repository implementation. It's injected with a Mongo template. The add method just simply calls insert on the Mongo document, passing in the restaurant, sorry, on the Mongo template, passing in the restaurant and the name of the collection. And then under the covers, the template is using bean introspection to turn that entity into a Mongo document and storing it in the database. And then the find method is constructing a simple query where the ID is the passed-in ID, and the target class is restaurant, and the collection is available restaurants collection. And so it's calling the Mongo API to retrieve the specified document, and then once again using bean introspection, it's turning that document into an instance of the restaurant class and returning it. So you can see that by using the Mongo template, the actual Mongo data access code is pretty simple. And here's the corresponding Java config that's defining the Mongo template bean. And key things to note here is it's injected with a Mongo, which plays the role of a connection pool. It's somewhat analogous to a data source. So we've got two beans, Mongo and Mongo template. And there's also setting some properties on Mongo template, but that's just a minor detail. So using Mongo, as you can see, is pretty straightforward, both in terms of the mapping from your domain model to Mongo documents, but also because of Spring Data for Mongo, the coding is quite simple as well. So what about Cassandra? So the unit of storage in Cassandra is a column, which is a triple consisting of a name, a value. So in that regard, it's like an entry in a hash map. And it also has a timestamp, which is like the last update time. The thing to note is that even though we're calling this a column, the column name is just data, just like the column value. So it really is like an entry in a hash map. And the supported data types are numbers and strings and booleans and timestamps, as well as a composite type that, as the name suggests, is a sequence of primitive values. And we'll see an example of that later. And then a collection of columns forms a row that has a row key. So you can think of each row as effectively being a map, except that each entry also has a timestamp in addition to a key value. And then each column, then a collection of rows forms a column family, which it's kind of like a table. And then a collection of column families forms a key space that's somewhat like a schema in the relational world. So we've got columns, rows, column families, and a key space. Then in terms of operations for manipulating data, there's, excuse me, there's an insert operation that takes a key and then the column name, value, and timestamp, and then inserts that column into the specified row, or if there's already a column there, overwrites the existing value. So that's the way of getting data into Cassandra. And then the way you get data out is through a slice operation. And that works on a column family. You specify a row key, and then you specify a start column name and an end column name. So then what you get back are the columns within the specified row whose names fall within the specified range. So in this example, because the start column is N2 and the end column is N4, you get back columns N2, N3, and N4. You don't get back column N1. So very different from a relational database, quite different from Mongo as well, but it's actually quite flexible. So how can we use this to store restaurants? So there's a couple of different schemes that we could use. So one is simply have one row per restaurant aggregate, and then for each attribute of that restaurant have a column. And that works quite well for simple valued or scalar valued attributes like name and type. You just have a corresponding column. But what about collections? So one way of dealing with that is to have a column for each collection element. So in this case, we're looking at service area, and the name of the column is you can think of it as the path or the expression that you would use to access that particular collection element. So we've got service area paren 0, service area paren 1 as the column names and the corresponding values. So it's different, but it's a pretty straightforward way of mapping sort of a somewhat rich, nested, recursive domain object into this flatter key value world. And then we do a similar kind of thing for the opening hours, where it's opening hours paren 0 dot sub-attribute name, so day of the week, open time, etc. So that's a pretty straightforward way of just mapping the restaurant into a row and a column family. The other option is to use a single column for each entity and just to simply serialize those values. So either using JSON or Java serialization or XML, whatever your preference is, basically. And I found that actually works quite well. I mean, it's fairly trivial to using things like Jackson to serialize, deserialize to from domain objects. And also from a performance point of view, because there's actually fewer columns in the database, I've seen that it can perform fast as well. So that's the one I've used in my example. So in terms of coding, so Spring Data doesn't yet support Cassandra. So I ended up creating my own Cassandra template, and that's actually written using the Hector, brother of Cassandra, Java client library. And so as you can see, the code here is quite simple. So add method calls insert entity, specifying the key space, the column family, and the restaurant. And then under the covers, it's serializing the restaurant into JSON using the Jackson library and inserting the corresponding column. And then the find details by ID method is doing the inverse operation. There's a lot of coding underneath that I don't really have time to go into. So the key thing here is, well, I'm just using the Hector library. So, okay, so that's Mongo, Cassandra. So what about VoltDB? Well, that's interesting, because on the one hand, it's a relational database, so I can use the original database schema. That works, and I can use pretty standard SQL statements as well. but there's no JDBC, and instead you have to write stored procedures in Java, so it's not so bad, and invoke them through a proprietary interface. And then you also have to come up with a partitioning scheme for your data, since that's how VoltDB achieves its scalability. So stored procedures are a pretty integral part of how VoltDB works. So for instance, replication works by executing a stored procedure on each of the replicas of your data. Logging works by recording stored procedure invocations. And so when the database is doing a recovery, it actually goes through the log, re-executing your stored procedure to reconstruct the latest state of the database. And then also stored procedures invocations are transaction boundaries as well. So you invoke a stored procedure that begins a transaction, and when the stored procedure returns, the transaction is committed. So VoltDB, stored procedures is just sort of an integral way of how VoltDB works. And then the other thing you have to do is when you have to identify a partition column for each of your tables. So in my example, I started off by using the restaurant ID as the partitioning scheme. And this is really important for performance and scalability. Because so, for example, if I have a VoltDB cluster comprised of 3 servers, I then decided to have 2 partitions per server. So that's a total of 6 partitions with in this case with a replication factor of 1. So there's 2 replicas per partition. You end up with a scheme like this where partition 1 resides on server 1 and 2, partition 2 resides on servers 2 and 3, and then partition 3 resides on servers 3 and 1. So your data is sliced up by partition key and spread and partitioned across the servers, and then also replicated across the servers. And then another really important concept here is the idea of a single partition procedure, where that would work on rows that reside within a single partition. So for example, if you're doing a select from restaurant where you're doing retrieval by a particular partition key, that can just be executed very, very efficiently against a single partition. It just looks at the input parameter and says, oh, that SQL statement and the stored procedure needs to be executed over there. Whereas if you are accessing by something other than the partition key, like in this example, I'm doing a lookup by name, that stored procedure needs to be executed against all of the partitions, and then the results merge together. And as you could imagine, there's a lot more communication and coordination overhead, which actually makes it relatively slower. So what I found is single partition stored procedures are roughly 10 times faster than multi-partition stored procedures. So partitioning is really, really key here. And so I chose restaurant ID, so both in the primary key and also in the foreign keys as the partitioning scheme. And I got some pretty good performance, like roughly 10x faster than MySQL. At least. In some cases, it was even 20x faster. So it was pretty good. And here's a simple stored procedure. So you can see that you actually have to statically declare all of the SQL you're going to execute by having these final variables. And then the run method is just queuing up the stored procedures and then executing them. Here's the corresponding DAO or repository code, and the interesting thing to note here is that you have to do some work to take your and flatten it into a set of object arrays that can then be passed as arguments to the stored procedure. So it's it's slightly tedious to do that, but I mean it's just sort of simple coding. And then here's the implementation of the template class that's using the VoltDB client API, which is pretty simple. You create this client object, And then the basic way you execute a stored procedure is by going call procedure, passing in the name, and then the parameters, which are either simple values or object arrays. So no JDBC, but somewhat different. So in the interest of time, I'm going to skip over the configuration of VoltDB and kind of move on to talk about queries. So, one of the key queries is finding available restaurants. And so available in this context is a restaurant is available if the zip code of the delivery address is in the restaurant service area and the restaurant is open at the delivery time. And you can imagine that this query gets encapsulated by a finder method, find available restaurants, that takes the address, takes the delivery time, gives you back a list of available restaurants. If you're doing this with a relational database, it's a pretty straightforward three-way join between the restaurant, time range, zip code tables. Pretty, just pretty standard stuff, and the equivalent would be in Hibernate query language or JPA query language. With Mongo, it's actually also quite straightforward to do the same query. Because we've got all of everything is in a single document. We don't have to deal with joins, right? And Mongo has the query API is basically query by example, where you create a document that looks like the ones that you're looking for with some extra sort of markers in there. And so in this case, I want to find restaurants that are in the 94619, so I have a service area that contains 94619. So I have a query document whose service area attribute is 94619, and then I also want to find a restaurant that's open on Monday at 6:15 p.m. And so I say opening hours, and then $LM match means find an element that matches this subdocument where the day of the week is Monday, the opening time is less than or equal to 18:15, and the closing time is greater than or equal to 18:15. So it's not SQL, but it's a pretty expressive document-oriented query language, and then you just pass that to the query API and iterate through the documents you get back. And then in order to optimize the execution of that query, you just, in the same way that in the relational world we define an index to make things go faster, you do the same thing here, and I found that defining an index on service area worked quite well. And here's the code that executes this. So there's really two things going on. First off, we're creating a query, and it's like using the query helper class where the service area is zip code of the delivery address and the opening hours .lm match blah, so on and so forth. And then you pass that query to the find method that executes it and then takes each document that it gets back and then maps it to the and gives you back an instance of the available restaurant class. So as you can see with Spring Data, it's pretty straightforward to execute queries like this. So, but how on earth are we going to do this with Cassandra? Because if you think back, the basic operation we have for retrieving data out of the database is a slice operation. So that query is sort of semantically a very long way away from a slice. It's got joins, it's got multiple equalities, it's doing a less than and a greater than. And what turns out, what we have to do in order to support this is basically implement an index, another column family that contains, in essence, a denormalized version of the data that can then be queried using a slice operation. So this is very different than the relational world, and you end up in a situation where queries, how you're accessing the data, drives how you represent that data. And so what I want to do is step through how we can simplify the query in order to get it into a form that matches a Cassandra slice. And so the first way we can simplify the query is by denormalizing the data. So we're pre-joining it, so the SQL no longer contains any joins. Big simplification there. The other thing we could do is simplify the where clause by not worrying about opening times. So we just forget about it. So that means that the query is going to give us back more data that we then have to filter out at the application level, which is, not what we're used to, but it kind of helps us simplify it to work with Cassandra. And then the other thing we need to do is, well, there are multiple equalities in there, and let's just combine them into one by pre-concatenating the data. So instead of, so basically we concatenate the zip code and the day of the week, and that just gives us a single equality operation. And so in order to find restaurants that haven't closed at the delivery time, we end up with a very, very simple query where there's just no joins, one equality, and one less than. And this exactly matches the capabilities of the slice operation. Because if you think about it, that does an equality lookup and by row key, and then a range lookup by column name. And then, so we can take this data that we sort of denormalized in our table and map it to a column family. So the zip code day of the week is the row key. The closing time becomes the one component of the composite column name. And then the opening time and the restaurant ID becomes another component of the column name. And then the column value is the JSON representation that we need to get back to display the user. And so once we've mapped this data into a column family, we can then query it using a slice. And so in this case, if it's serving 94619 on a Monday, that becomes the row key, and then the start column name and the end column name basically becomes 1815, the delivery time, and midnight, effectively the end of the day. And with this sample data, that would give us back the Ajanta restaurant, and we can look at that and see that the opening time of that restaurant is 5:30, which is before the delivery time, so we know that this restaurant is open. So as you can see, we've managed to take what seemed like an impossible SQL statement, and actually by denormalizing the data, we've managed to get it into a form that can be queried using Cassandra. And, obviously we have to write some code to maintain, there's a fair bit of code to actually maintain the index, but it's quite doable. And, probably at this point you're going, gosh, what the heck did I just do? So I will let you read this slide briefly. So we're not exactly implementing a distributed map reduce function in Erlang, but we're like doing an awful lot of work here. But, effectively what this gives us is, because Cassandra lets us very easily build a highly distributed, highly scalable database infrastructure, unlike almost any other NoSQL database, we can leverage that in our application. Admittedly, we've got to do some coding, but there's tremendous benefits in doing that. So, if you need to be distributed across multiple data centers, or you need to scale to many, many servers, that little bit of coding is worthwhile. Okay, so a few minutes left. So I want to talk very quickly about VoltDB. So when I started off, I thought, well, VoltDB is relational, so I can just take that standard three-way join SQL statement and run it. But it turns out that it doesn't perform well. So if you don't create the necessary indexes, it runs, but it does full table scans, which is incredibly inefficient. And then if you create the required indexes to make it go fast, at least in theory, it doesn't actually make it through the VoltDB compiler. So VoltDB is not quite there yet when it comes to supporting that statement. And in general, this is a hard problem because you're doing these joins not involving the partition keys in a distributed database. So this, in all fairness, is quite a hard problem anyway. So then what I did is actually I denormalized the data to remove the query. So inserts were actually really fast still, barely impacted performance, but queries were only slightly faster than MySQL. So that was a little disappointing. So on the one hand, inserts, great. Queries, not so good. So then I switched it around and I picked a different partition scheme that made looking up, finding available restaurants a single partition stored procedure. And that meant that the queries were really fast, like, 20, 30 times faster than MySQL, but it turned the adding of restaurants into a multi-partition stored procedure, which really slowed down the inserts. So we sort of kind of end up with a situation where we can't find a partition scheme that's really good for both queries and inserts. We kind of have to pick which one we want to optimize for, which may or may not be good for your application. You could argue that in many applications you want to optimize queries, but that really depends. So that's effectively my talk. So kind of in summary, it's sort of like relational databases. They're great, but there's limitations in terms of affordable scalability and ability to distribute, plus data model limitations. NoSQL databases solve these problems, but you have to give up like ACID transactions. And then as you can see, querying some of these databases is a non-trivial thing to do, even though they give you incredible scalability. And then a NewSQL database can give you ACID transactions and in some situations incredible performance, but not always. And obviously you can't use JDBC. So you've sort of got each of these. You've got some really, really interesting trade-offs. So it's kind of like, well, you got to, if you are going to go down this sort of move away from a traditional relational database, you kind of have to think really, really carefully about which one is the best fit for your application, and do some significant proof of, prototyping, proof of concepts, and so on. And then maybe you should consider having a polyglot architecture where different modules can leverage the strengths of each particular database. And then, and the other interesting thing is where if you're a startup where you're still you don't really have any users and so scalability is not yet a problem, maybe you should avoid all of this and stick with a standard relational database so that you can iterate faster using robust, proven relational database technologies like Hibernate and JPA and all the other frameworks that build upon them. So, so it's really, really interesting state of affairs. So that's my talk, and I would like to thank you for listening, and I hope that you found it useful. And then I'm just going to take some questions. So one question I have had is, so if I'm building a website which provides sort of information about just browsing product databases, is NoSQL a good fit for that? And it kind of depends in sort of on the exact nature of your application. I mean, it could very well be in the sense that NoSQL databases scale, for example, incredibly well. And so, for a lot of sites, scalability is a problem, and NoSQL databases solve that. But, I think with all of this, you kind of have to dive deeply into the actual nature of your application and the database access methods, the ways it's accessing the databases, the queries, and so on, and see which ones are really the best fit. Another question I had is sort of live applications which sort of use these various databases. And so if you look at Cassandra, for example, that was developed by Facebook to support their inbox search mechanism. It's pretty much, if you go look at any of these high-volume sites, they're likely to be using a NoSQL database in there somewhere. So I think like GitHub is using Redis, and so on. So it's just pretty much that they're used quite widely. Obviously, Amazon have DynamoDB that they're using internally, and so on. So another question is, well, what are the main advantages of NoSQL? And just to sort of reiterate there, I mean, it depends very much on your use case, but it tends to translate into better performance, better scalability, and a richer data model, particularly in the case of a document-oriented database like Mongo. And then also just the schema-less nature of them can be advantageous, and including the support for semi-structured data as well. Then another question I had is, what are these available without cost? So these are all open source databases, so you can just download them, start using them. Though, as you could imagine, that there are various vendors or companies that are offering support and commercial versions and the enterprise versions with additional features as well. Someone asked about, well, who's using Cassandra? Actually, one of the really interesting companies that's getting a lot of attention right now for their technology stack is Netflix. They sort of, you look back a few years, they were 100% in-house using relational databases, and they've migrated to the cloud, namely Amazon, and so they're leveraging Amazon's data centers spread across the globe, and they're using Cassandra very heavily for a lot of their mission-critical work. And so they're a great example of a company that sort of embraced the cloud and embraced NoSQL databases. Someone was asking about performance of Mongo and versus Cassandra. And in my sort of informal benchmarking, that what I found is that Mongo was generally incredibly fast, but particularly when it came to doing inserting. I sort of had two benchmarks. One was really measuring the performance of adding restaurants to the database. The other one was analyzing the performance of retrieving restaurants both by primary key and also finding available restaurants. And so Mongo was generally pretty fast at inserting and looking up by primary key. And it was still much faster than MySQL at doing find available restaurants, though it was not sort of the same level of improvement when compared with primary key-based lookup. And Cassandra was generally faster than MySQL, but not quite as fast as Mongo, though I'm a little suspicious of how I'd configured it. So someone was asking about, is spatial data supported? MongoDB supports geo-search, just sort of like kind of natively out of the box. So that's definitely there. The other ones, you would have to build on it, though I know at one point there was a company, Simple Geo, that was, I think they were building their geo databases on top of Cassandra. Oh, someone was asking about delete operations in MongoDB. Yes, so you can delete a document. So sort of the basic operations like adding a document, updating a document, and deleting a document. Another question was about, well, suggesting guidelines for figuring out which ones to use. And kind of the main thing I'd say there is don't blindly just go pick a NoSQL database because you heard that they were really cool. I got the impression that a number of people have been doing that. And the trouble is that you might end up in a situation where that NoSQL database is not actually a great fit for your application, in which case you're going to be in a world of pain. So I think it's just really, really important to do a proof of concept. Think hard about how your application is going to access the data in terms of queries and so on, and then see how well that fits with the capabilities of the NoSQL databases that you're evaluating, and to do a proof of concept. So I think on that note, I'm going to end. And so I want to thank you all for listening, and I hope that you found it useful. Thank you.